So in the section called Percent Yield, Advanced Practice Problems Using Stoichiometry, the previous problems gave you the theoretical yield values. In the remaining problems, you'll have to calculate the theoretical yield using stoichiometry. Problem number 6 says, if the reaction below uses 20.0 grams of lithium hydroxide and an excess of potassium chloride, how much lithium chloride could theoretically be made? So let's take a look at what this problem entails. Uses 20.0 grams of lithium hydroxide, that's this substance right here, and an excess of potassium chloride. Now when you see this, an excess of potassium chloride, that's this right here, that just means you have plenty of it and it's not going to run out. Basically that means just ignore this substance. Okay, so excess means you don't need to factor that into the problem. But the next part of this question says, what we're trying to find is how much lithium chloride could theoretically be made. So lithium chloride is this substance on the product side right here. So once you've identified what you're starting with, in this case the 20.0 grams of lithium hydroxide, and you figured out what you're trying to get to, in this case how much lithium chloride could theoretically be made, now we can begin our work, double checking of course that our equation is balanced to begin with, because if you don't have a balanced equation you're not going to have the correct mole ratios to make this problem work. But fortunately this equation is already balanced for us, and we recognize that this equation is just a 1 to 1 to 1 to 1 ratio. Alright, so what we see, we're starting with 20 grams of lithium hydroxide, so I'm going to recommend that you start by writing that number down all the way to the left of your paper, because sometimes these problems get kind of long. So you're going to start by saying 20.0, labeling the unit grams, and labeling the chemical formula. This is LiOH. Because here's the problem, we're going to be starting out this problem talking about LiOH, but ultimately we're going to be talking about LiCl. So we need to know which substance we're talking about. The first thing we need to do in these problems is, because coefficients in a balanced equation do not represent gram ratios, but they do represent mole ratios, our first job is to take our grams of our starting substance and convert it into moles. Well, you've done this plenty of times. Converting grams to moles, we're going to put grams of LiOH in the denominator, so that will cancel. And we're going to put 1 mole of LiOH in the numerator. Okay, so this problem right here, we need the molar mass of LiOH. And so if you add up the mass of lithium from the periodic table of 6.9, oxygen from the periodic table 16.0, and hydrogen at 1.0, altogether that is 23.9 grams. If we stopped this problem right here, grams of lithium hydroxide would cancel, leaving us with moles of lithium hydroxide. Okay, moles of lithium hydroxide is not our final answer. We're looking to have how much lithium chloride could theoretically be made, and by how much I'm going to clarify in grams. So the next step, once you have moles of the substance you're starting with, right, so we know moles of lithium hydroxide, we can use this ratio of 1 to 1 to predict how many moles of lithium chloride we can make. Because it's a 1 to 1 mole ratio, that makes our math really quite simple. So to make sure our units cancel, we put moles of LiOH in the denominator, and in the numerator we put moles of LiCl. Now from the balanced equation we know it's a 1 to 1 ratio, so those ones are coming from the coefficients of the balanced equation. Well, if we stop this problem right here, moles of lithium hydroxide will cancel, leaving us with moles of lithium chloride. Well, we're going to try to convert this all the way to grams of lithium chloride, so we need one more conversion fraction where we're going to put moles of lithium chloride in the denominator and grams of lithium chloride in the numerator. All right, so 1 mole of LiCl, add that molar mass up, and we get 42.4 grams. All right, so we see the units of moles of LiCl cancel, leaving us with grams of lithium chloride. And the math, of course, is going to be 20.0 divided by 23.9. Hit the equal sign. Nothing really to do here with the times 1 or divide by 1 because that's not going to mathematically change it. But then we'll multiply by 42.4, and what we will end up with to 3 significant figures is 35.5 grams of lithium chloride. All right, so this right here, this stoichiometric answer, which we've already done some practice with, this is our theoretical yield. Theoretical yield is determined through a stoichiometric problem. Now, part B of this problem says, after doing the above experiment, the reaction produced only 6 grams of lithium chloride. What is the percent yield of the experiment? So the actual yield done at the lab bench is 6.0 grams. We're going to divide that by the theoretical yield of 35.5 grams, and then multiply by 100. Our answer is going to be limited to 2 significant figures because of the 6.0. And we're going to see once you get that out of your calculator that that rounds to 17% yield. So a low percent yield, but that's all right. This is just the way this particular experiment went down. Okay, let's try the second problem, or actually problem number 7. What is the theoretical yield of iron 2 chloride? That's this substance right here. If the reaction below uses 34.0 grams of iron 2 bromide, that's this stuff, and an excess of potassium chloride. So potassium chloride is in excess, so we just ignore that. So starting with our stoichiometric problem, we're going to start with the 34.0 grams of iron 2 bromide, that's FeBr2. We're going to do our 3-step stoichiometry problem, so grams to moles. So grams of FeBr2 in the denominator, 1 mole of FeBr2 in the numerator. Adding up the molar mass of FeBr2 to the nearest tenth is 215.9. Our second step is going to take moles of FeBr2 in the denominator, and we're going to convert it to moles of our final product, which we're looking for, the FeCl2. Now the numbers that are going to go in here are going to come from our balanced equation. Since this equation is already balanced, we see it is a 1-to-1 ratio, so that keeps our math pretty simple. And then our final step is going to be to get rid of the moles of FeCl2 and convert that to grams of FeCl2. 1 mole of FeCl2 adds up to 126.8 from the periodic table. Watching the units cancel, grams of FeBr2 cancel. Moles of FeBr2 cancel. And moles of FeCl2 cancel. All right, so if we see we have our fewest number of sig figs are going to be the 3 sig figs that we had back here in our original measurement. The number 1 moles that we see here, those are counts and those are not measurements, so we're not going to let that limit our rounding. And so to 3 significant figures, our calculator answer should be rounded to 20.0 grams of FeCl2. So that is our theoretical yield. If we then take this theoretical yield of 20.0 grams and use it in our final question here, what is the percent yield of iron 2 chloride? If the actual yield is 4.0 grams, so our actual yield of 4 divided by 20 grams, multiply that by 100, and of course we are going to get 20%. To make sure that we have 2 significant figures here, we will put a decimal point there, and then we have 20% there. All right, so there are 3 more problems I think here on the rest of this problem set for you to try. I will not post the work here, but you will be able to check your work in the classroom. Well, this has been a presentation on percent yield using stoichiometry. We'll see you in the classroom.